Okay, so welcome. Sorry, I had to get a few things in order. First of all, my VM somehow got screwed up, had to fix this, and then, I don't know, the streaming didn't start, had to do the credentials on YouTube stuff again, but now I hope that everything works. So please just verify really quick to me that the audio is fine, that the video is there, and then I hope that we can head into the CTF challenge. So I keep talking a little bit until I get like a little bit of feedback that everything seems to work. So as you can see to the right of the screen, I try to structure a little bit the stream, that we just start with an intro, what the challenge is about, and talk a little bit about the 33ctf. And then we will have a look at and then I try to move the red ball a bit further, and we will look at the actual implementation. We'll have a look at the binary, have a look at how it works, what it can do, and try to learn a little bit the functionality of the code. Then we start with debugging. So we are actually like use GDB and step through it and try to understand the code on a deeper level in order to get a picture and an attack idea. And then we want to do the actual pwning part, where we develop the exploit and get ultimately the code execution, and then we will just, I don't know, wrap it up. So the challenge I'm gonna talk about today is from the 33c3ctf that happened in December in Hamburg, and this was the first time that with my CTF team we played as a group actually at a location and not just remotely, everybody at home. So that was so much fun for us. And yeah, the Baby Feng Shui challenge was one of the challenges that we solved. I wanted to prepare a video for this, like I did for the other two videos I already did about the 33c3ctf. But then I got bored and decided, oh, you know what? Let's try this as a stream. So and that's. I hope that will go well. I have one more video write-up coming from the CTF, which is the Ho challenge, which was also quite fun. And otherwise, yeah, so let's have a look at it. The challenge is called Baby Feng Shui, and the description reads that they asked me to write the best application to store our user profiles, so I did, because I know how to do this stuff, because believe me, I'm the absolute best when it comes to memory management here. I will even let you try to hack it. And then they give you a tar file with, let's have a look at what it actually comes with. It comes with the binary itself, and they also give you the libc, which is very, very convenient. And it's also 32-bit, which also makes it easier for beginners to use tools, because oftentimes some free tools only allow 32-bit and things like that. The challenge is also called Baby, which, if you are not familiar with CTFs, then baby challenges are usually intended to bridge a gap for people that either started or are like just understanding it and are a little bit intermediate. So these are intended to be easier approachable than the high point pwnable challenges. The other thing is it's intended for kind of beginners, but it's still kind of hard. It's not the standard buffer overflow, but it's you would be able to solve a challenge like this if you, for example, follow the videos I've done up until now. If you follow the binary exploitation series, from exploitexercise.com, if you do the protostar stuff and you understand this, then you should be absolutely able to solve this yourself. So it requires already some form of dedication and time you have spent in about this, but then you will be able to do it. So about the title, this already tells you a lot what it will be about. First of all, baby, that it's easier. You should be able, something you could maybe try. And then Feng Shui is already a very good hint what it will be about. And obviously that will already help us when we look at the binary because that information helps us already to guess what the challenge is. People are saying that my mic is muted. Maybe, okay, wait, let me. Is it just extremely quiet? Should I like? Ah, fine. Thanks, guys. Anyway, so Feng Shui, if you just type that in, exploitation Feng Shui or something like this, you will find that it has something to do with heap stuff, Heap Feng Shui. And there's even a Wikipedia article about this, and it tells you that in computer security, Heap Feng Shui is a technique used in exploits to get arbitrary code execution, and the technique attempts to manipulate the layout of the heap by making heap applications in carefully selected sizes, and therefore like manipulate and control the layout of the heap. So just by knowing this, you already know that you will have to look up for heaps things. You have to look at the heap, what exact kind of objects are allocated on the heap, and their sizes maybe, and that you might have to think about a special arrangement of them. And with that in the back of your mind, you will already have a way easier time approaching this binary. Yeah, so let's just execute it and try to understand a little bit what it does. I moved now to code here. So I'm running here on a Mac, as you can see, but I'm running this Linux Ubuntu VM. So I'm able to execute this Linux binary. So when you execute it, shit. Okay, so as I said, my VM got nuked, and I had to reinstall everything, and now I missed the 32-bit Ubuntu libs. I don't remember how to install it. So if you like, it's like one of these weird errors that could like completely stump you for a long time. If you see that you have an executable, it says that it's an ELF executable, but it says exec format error, and it's like one of these things that you could like spend ages on, but it just means that you miss the 32-bit libraries. I don't know. I have no idea if those are the... Okay, no, stop, I'm an idiot. This is my Vagrant VM on the left. So there we go. I thought I had it installed. Yeah, now it works. Okay, forget that. That didn't happen. So let's execute it and have a look at this. So there's a menu, and this menu you can select different kind of actions. Apparently you can add a user, you can delete a user, you can display the user, and you can update its description. So fairly simple. Let's just make some examples. An alarm. So that is already quite interesting. This is used during CTF challenges. I guess that's why it's used, is to in case a process hangs, the alarm that is initiated at the beginning will cause will cause a process to be killed after a certain amount of time. That helps against, like, if you accidentally make a faulty exploit that, for example, ends in an endless loop or something like this, or just somebody is like leaving the connection open for a long time. So that's just helping for the CTF challenge to clean up and be more stable for the players, but it's obviously annoying if you locally try it out and after a couple of seconds already it dies. So one first thing would be to just patch out the patch that, and yeah, so that it wouldn't trigger the alarm anymore. So I guess it's already like a first quick look into the assembler code, but doesn't matter much. Here's the main, and it's this is not an anti-debugging thing or anything that should prevent you from solving this challenge. It's literally just like to make it easier for the people running the challenges, I think. Maybe I've seen some people in the chat who were organizers, which is great, can maybe confirm or explain what it's really about. Anyway, so you can just like ignore that call to the alarm, and this way the alarm will never be set up. And then we just save the modified version of that. So so now we should not be bothered by it anymore. Okay, so we can add a user, and it already asks us for the size of the description. And if you already remember what Heap Feng Shui is about, that you try to manipulate sizes of certain heap objects to rearrange them however you want, this is already like a good hint. Maybe you control here size of an allocation or something. So let's just do like 8 and then enter a name and then a text length and a name. Okay, so let's display this user. We have to select an index. Choosing indexes is obviously also something you could be you could take notes of, because maybe there's like an issue where you could enter a number or like out of bounds, like bigger than the array is that is holding all these users or something like this. So this is obviously also something you would wanna have a look at. But yeah, so I just selected the user, the 0 user, the first user, and it just prints everything. Of course, when stuff is printed, you could also test things like what happens if is there maybe a format string issue. But yeah, that is not the case here. But these are the kind of inputs you see what kind of inputs you have, and what kind of response you get, and think about what could potentially here be things could happen. So we could also try to display a user that is out of range, like 99. We didn't do this, but didn't do anything. So maybe it didn't at least crash. So it's not just an out of bounds read, probably not an read somewhere from random memory that is completely bad, I guess. Maybe. Who knows? Then there's an update user description, where we then also have to select which index, and so here's the first user. And now, and the interesting thing is, now it asks us again about a text length here. So we always chose here the text length 8. So you could ask yourself what happens if you try a longer text length, for example. And then suddenly you get something like, my lead defenses cannot be fooled. So that is already, whoa, what's going on here? Why does it allow me to specify a different text length for a description, and why does it fail when I get here something bigger? So all these kind of things you take, maybe you have a paper next to you and you write all these interesting things down that you want to have answered later. Yeah, so let me quickly have a look at the chat just in case some questions came up already, and then before we move on to actually look at this in the disassembler. It's lagging super hard. I'm sorry. I hope it will be all then fine on YouTube later in the archive when you look at maybe later. Okay, no questions so far. Great. So let's. In this case, I use Binary Ninja. I still not very proficient in all of the different tools, but it's one. Binary Ninja is the one I used more often recently, so it's just like the thing I choose right now. It's not like that I could unleash the power of IDA fully anyway. Okay, so as I said, it loaded us here in the start, and something I haven't explained in a video yet, but it came up as questions before, is what happens if there are no symbols, like if the binary is stripped and you don't know where main is, you can't just disassemble main, or the name is just not registered as main. At least like those, at least in those CTF channels where you have like regular GCC compiled C code or whatever, there's a start function where that's the actual entry point of the binary. So there's something running before your actual main, and that is, you will see this pattern everywhere. And the first argument that is given to call libc start main, which is implemented in libc and whatever, eventually will end up in this at the address that is passed here as the first address. So whatever this is, like if that's just garbage, you know, this is then the main, the first argument here. So okay, so here we can immediately see that with puts is obviously printing a string, that here it prints the menu. It prints a string here, add user, delete user, display user, and so forth, and then the action, and then it uses scanf to read your menu selection. And the string here seems to be not properly referenced as a string, but you can see here that it's just %d, so it's reading an integer. And then usually the value in this case that contains now the value, the integer that's read. If you look at the main page for scanf, you see that it returns the integer, and then if we look here a little bit further down, you notice that here after initial check if that was successful or not, what am I talking about? Let me check scanf again. Right, exactly. The return value is just the just like an indicator if it was successful or not, and the return value is usually on 32-bit in then EAX after this executed. So it's just checking if basically that scanf was successful or not, and then the actual value is then written into a value on the stack. It's basically similar to printf, which takes values from the stack and prints them. Scanf will read this number and puts it at that location on the stack, depending on how many variables you have after your format string. And then it moves that. Basically now here you have the integer, so you can like menu action. That's the from the user read menu action. And then it's just checking is this test EAX will basically just check if EAX is 0, and if it's not 0, it will jump all the way. It will jump down here. It will skip this whole block. So if it was 0, that would be then the first menu selection, and then it would print the size of the description, it would ask you for the size of the description. It would scanf that and then call another function here. So, and that matches exactly what we have observed when we executed the binary. It after asking us for the option, when we select 0, it asks us for the description. So here it's waiting for the scanner for the size of the description. We enter something and then it asks for a name. It's obviously not here, so it must be in this function here. And that is a bit longer function, but yeah, that seems to ask us for the name here, and cause then again some other functions. Here you can also notice already malloc, and then like this is the heap feng shui stuff. So here starts to be things allocated on the heap. So you know you are on the right track. So let's have a look at the other thing. So here's then obviously again the menu action load in EAX compared with 1. So this is then the next option. Then here is compared with 2. This is then the option 2. And this is just the menu with ifs and else and checking what value you entered, and then it will call the corresponding stuff that handles that menu point. Anyhow, let's have a look at what it means to add a user, because obviously that will be a very important part. And thus, after we read the size of the description, this value, again, like here's the scanf, this variable here is the size of the description that is read from the user, is placed on the stack, and then this function is called. So this function is called with the size of the description that you entered. And then we can see what it's happening, what will happen with it. I guess that should be the size of the description that is read from the stack into EAX and then loaded into this local variable. So I guess that should be the size of the description. And then that size of the description is then pushed on the stack for a malloc. So here you already control the size of a malloc. So let's note this down. Let's start like with basically our exploit, and just oops, what happened? Tools. Okay, so there we go. So with selecting a new user, we will be able to call a malloc with our controlled size. Then we have a memset here, rather unimportant, and then there's a second malloc. And here it will allocate a fixed size. It will allocate hex 80. So after that, after we allocate our size, it will malloc hex 80. So, and then, it memsets probably that. So, okay, malloc will return the address where it allocated the string, and then it will be stored in var14, and var14 will then be passed to memset, so that will then set the whole memory there to 0. And I guess this also happens up here. It gets var18, which is the return from the first malloc here. So and it gets all set to 0. So this is basically a 0 alloc. It will allocate and then overwrite everything with zeros. So after the memset here, we know that var14 is the allocated hex 80 size, and the var18 is from the previous alloc, so it's our description size, not description size, our description allocated chunk. So these two will be moved into registers to work with them now. And then it writes the address from the description chunk at the address of the fixed allocated 80 size chunk. So that's quite interesting. So here is basically the object setup. Don't worry, we will step through this in a second, and then you will exactly see this visually in the memory that what it's doing here. Then it does here something with global variables. I'm not going into complete detail here. I think that's not necessary. It will basically here then also have an array with how many users are registered for the index, and it will, you see here like a typical index of like an array offset move where it, depending on how many users you have, that's the number of users in AAX times 4 plus the base address, like this is then a big global array that is used to store all the allocated users. So yeah, we don't need to understand it like line by line, the assembler code, what it does. But after you allocated all this chunk, it asks enter now the name, and then yeah, we will debug this because it doesn't matter so closely. So this will allocate new user with hex 80 or something. And then this other function here, let's have a quick look in here. So that seems just to be a function that is reading. It seems like fgets, and then it looks up for a new line, and then probably like writes a 0 to where the new line was. So that is just like a read input function, I guess. Down here we have another function that seems a bit more complicated, a bit bigger, but let's quickly just scan over like what could it do. It asks for the it prints a text length and reads then the input of your text length. Okay, here's apparently some kind of check. Again, here you see the global. I guess that's the user array. Like again, we see here the reference like in an index of an array. So that is probably the user array. And then so if here's look at this. So if this check, whatever it does, fails, it will print the lead defense cannot be fooled that we have seen before. So that is definitely interesting part that we want to have a closer look at later. Otherwise, if that was all fine, it asks you to enter the text and read again the input of your text. And then what does it do? Nothing. It will like return again. So this will, how do we call this? This will read text. Yeah, we'll read some text, probably also into the into the heap. Like we will figure it. We will see it in a second when we debug it. Okay, so I think now we have like a rough understanding that it allocates stuff on the heap, and it's way easier to understand this when you start to debug this. So I suggest we just open this in GDB and look at the heap and so forth. So we use the patched version GDB, and then let's just add a user. Size of description, I know, let's go with 16, and then we enter some A's, and then we make a text length of 16 and enter some B's, and then we press Ctrl+C to break, and then we look at where the heap is located. So here's the heap, and then we can have a look at this. And then we immediately see here our B's and our A's here. So we know that there are two mallocs, right? So let's take this really quick, like this. So we know that there's one malloc with a size that we choose. And the first object here on the heap, like this is the pref size, this is the size of the current chunk, and then this is where the actual data starts with our B's that we've entered. The size is hex 19, And first of all, this means the last bit is set, which means the previous block of the heap is in use. Look at my heap videos. It's not that important in this case. And that would be then in decimal 24, but we entered 16. So if we subtract 16 from that, so 16 data, we have 8, which is explained by the whole chunk is made of the 16 bytes that we chose that we wanted to allocate, plus 4 for the pref size, plus 4 for the own size, and that the whole chunk size is thus hex 19, or so to say hex 18. And then there are the Bs. So what was the Bs that we entered? The Bs were the text. So the allocation with our size is the text that we enter. And then the second chunk that we see here obviously starts then here and has the size hex 88, which is the hex 80 that was allocated, fixed size plus the 8 again for size and pref size. And then here is, oops. Sorry. So there we go. Here's an address that you see that immediately that the first word in this fixed heap chunk is an address, and it points at the start of the text that we entered. So this address here points to here. So we have two chunks, and the second chunk has the first word is an address pointing to the first chunk that we entered. And followed then by it are the A's, and the A's what we entered were the name. Okay, so that the name is thus placed in this text. So now you can already think about how could you exploit this. Like, what can you actually control, and what could be a goal that you would like to control. Let me quickly check the chat again before we think about this. Maybe you can think for a second what would be very convenient if you could control it. Oh gosh. Why? Okay, so first of all, you guys write a lot. Okay, about lagging. Sorry. I know it's boring if I just try to catch up with the chat. Is there a way to kick a person? I don't know. Like, I don't want to. Just ignore it. Doesn't matter. Man. So much wasted time reading this stupid chat here. I'm really sorry if I missed something actually important, because I'm just like flipping over this because it doesn't make any sense. Can you use AT&T syntax next time until syntax sucks? All the tools are Linux based anyway. I'm sorry. Like, I have a really hard time working with AT&T. It just looks so convoluted to me. I mean, you can just like, do it yourself and do the AT&T stuff. It's better for you anyway if you try to do it by hand yourself and try to just follow along rather than just watching my stuff. So maybe so you get motivated to do it yourself if I stick to Intel. You can input some text, and if you free the chunk, you free the address, I guess, and then you execute the text. So, I mean, you are kind of referencing the heap, where we actually exploit the heap in the exploit exercises stuff. That does not really work anymore. First of all, the heap is not executable on a regular Ubuntu system nowadays. Like, you cannot jump into shellcode. So he's talking about that we could like somehow screw with something and then place, instead of the text, place here shellcode that we execute, which we did in a video, which I did in a video that showed like very old school very old school heap exploit. But that doesn't work anymore because these addresses are not executable anymore. I don't know how we can make this visible here in GDB that it's not executable. But yeah, so that doesn't quite work. Also, to do the old school exploit, you would somehow need a way to corrupt heap metadata, and heap metadata are these information like the pref size and this size here. So you somehow would want to screw with this value here, or with let me pick another color. You would either want to screw with the size from here or here somehow. Otherwise, you cannot really screw with the heap algorithm. But I mean, maybe that's possible. So far, we haven't figured that out. But again, then you couldn't redirect code here. How far am I into my master's degree? I guess I take another year. I take it really slow. If you're American, we don't pay university fees in Germany, and I do work as a freelancer while doing it, so I have to balance university and working, earning money. So I just take the university as slow as I can, and try to learn a lot during this time. Yeah, try getting a co-host. Yeah, I'm sorry. Like, I don't know. I know, I'm sorry, with the moderation and stuff would be helpful. Anyway, okay, sorry. Let's continue. So, to recap, we have two mallocs. The first one, the length of it is controlled by us. We control the size of the first chunk, and we can write text there. So this is the first chunk here. And then there's a fixed size second chunk after it, which very interestingly has an address in the beginning which points to our first chunk. And now let's again have a quick look at what we note down. We wrote that the text of the first chunk were our B's, that was the text that we write, and the name was what is in here. And if we are in the menu, that was stupid. If you are here in the, so let's add a user again, AAA. What did I do? We had a user, AAA, text length BBB, and we update the user description. We select an index, and now we ask for the text length again. So we can go 16 again and take 2 C's. And now let's have a look at the heap. So to the right, you can see how it looked before, and now to the left, you can see how it's now. And you see that the text you update is in the first allocated area. And you can, like, just by reverse engineering it, or just by like guessing, or just like get a feeling for it, this pointer points into the start here, and you could maybe assume that this controls are right. We can try to verify this now. You would also realize this when you step more through the code here. So let's head actually back to adding the user No, let's have a look at update a user description, what it does. So there's option 3. So we look here for the compare for the 3, which is here. So it asks us for the index. Then it reads the a value, the index that we want, and then it, so in this case, it's not size of description, it's the index. The index is pushed on the stack and then read some text. So here now on the one argument here is which user you want to update, and you can see here again that now the value that, so this is the argument, this is the user index argument that is passed to this function. It's written into EAX. EAX is written into the local variable 20. So this is the user index that we want to update. And the user index is again then referenced here. Again, you get here the number, and then you get and have this user array here that you get in this case it's ID. The index is 0, so you will get the first value of the user array. Let's have a look at the user array in GDB. So we have allocated one user, and we can just have a look at. There's obviously only one value there. Let's just add quickly another user. So now there are two values, and we can now look at the heap again. The heap was here. So we have the first value in the address, which is our first user. The first address in our array, which is the first user, is points into the heap at this location here, which is the 80 allocated chunk. So that it points to the second chunk that was allocated, which is the fixed size, which contains the pointer to the first chunk. I hope that makes sense. And the second address then here points somewhere else onto the heap to B8, which is here. And you can see this looks basically exactly the same. You have here a small chunk allocated with, this is the small chunk, and then afterwards you have again a hex 80 big chunk, and the second value also points to the fixed chunk. Okay, so now we know that in EAX is the address of the fixed chunk that was allocated on the heap. So this value is now in EAX. It checks if actually there is a value. So if you would have entered an index that is very big, it would up here it also checks the amount of, I think that's the amount of users. Yeah, I think that is like how many users have already been added, and it checks if that's in the range of how many users was accepted. But there's also maybe a way to delete users, if I remember correctly, and then you want to check if that pointer still is a value, if it's 0. So if that address is there in the array, it will ask for the text length. And let's see again where. So user index. So you EAX. It will read the text length you want, and then again it fetches the address on the heap from the array, and then it dereferences the first value that is in the heap chunk again, which is this value here, and follows that one. So now this address is in EAX. So EAX is equal to this first user controlled chunk. That is the address, and it got this address by dereferencing by taking this address that is here. And then that is for now stored in EDX. So I guess it's better to say EDX has that value. And then we load another address in EAX, and that address is that's the size that is read from the user. So you enter a text length, and that is then moved here into EAX. That's the text length you enter, and then these two are added. So now you add on the address 08, you add the length that you enter. This means if it first pointed here, and if you would say I want a text length of 4, it would do +4 and would now point here. Or if you do +16, it would point here. And if you point a higher value, it obviously would point somewhere here. So that value is then in EDX. And then it takes the current user index again, gets again the address of the main object block. So this address here, this is where this fixed 80 sized malloc, that's like the big object that references the other object, so the main object, and moves that in EAX. And now it compares the address that was calculated, so the first block plus the length you entered, and compares it to where the other block is, where the main block is. And if that check is true, or for whatever, if you are below that, if your length doesn't reach as far as the main object, you will just continue, and you can now enter the text. But if the value you enter points way past the other object, passes way into the other object, which would mean if that would be successful, you could then just write a lot of data over it. You could control all this data. It would be exploitable because you could overwrite the size of the chunk, but you could also control this other pointer here. And then it would trigger the lead defense. So whatever happens here, it's interesting that it takes, that if you update the description, it will take the pointer of the main object, of the user object, follows it, does some checks or whatever, and if the checks are successful, you can write to that location. So if you somehow manage to overwrite or control where this pointer points to, you could point it to anywhere you want, and wherever you point it, if you would then say please update that user, it would follow that and would just go somewhere where else you control, and then you could just overwrite values there. So if you could control this pointer, this is amazing. Generally, it's always good to look for pointers you control. Pointers are extremely helpful during exploitation. Pointers and offsets, those are basically the things that you somehow try to control. Even the stack, if you look at the stack and you think, and the return pointer, for example, or even just the base pointer or whatever, are pointers that those are addresses that point somewhere. And if you manage to control an address that points somewhere, you can it's very likely that you can somehow take it over. So generally, that is always a thing you want to look for addresses you might be able to control. Okay. So let's quickly recap again what we have. When we add a user, we select a size, and we create a chunk of a size we control. Chunk size we control. Then immediately after that, it allocates a hex 80 big user chunk with a pointer. So the first element of that chunk has a pointer into the chunk we control. Chunk size, yeah. So into the first chunk. And you could do this again. Like if you add a new user, that would chunk 2 we control of the user 2, and it points to the chunk size we control. And then we just realized that there's a check if you allocate this chunk, but then select a size that would the address of this chunk plus the size you entered would reach further as this chunk, it would not allow you to write. So if you think about this check, what it does, it only checks the distance between these two and checks if the size you enter stops before this chunk. And here's where Heap Feng Shui comes into play. Think about what would happen if this chunk that its address is checked to against with the length is not here, but is actually here. We don't know yet how we get there, but if that were the case, and we would think of the check that is implemented, you could add a big number that reaches over this other stuff here and stops before the blocks that it's checked with, and it's perfectly fine. It will not trigger the defense, but you will be able to completely write over this stuff here. And if you manage that, then you can override the pointer of the second chunk here, and then you can control the write destination when you update the description, and you can write somewhere wherever you can write just wherever you want. Okay. Are there any questions so far? I know it's probably super hard to like follow and stay concentrated. I'm rambling a lot. It's easier to follow a 10-minute video, I guess. But I don't know, maybe there's a chance that somebody can like has a question or something. So how could we get there? Let's have a look again at the functionality of the functionality of the program. We can add a user, that is fine. We can display a user, that probably doesn't help us much. We can update a description which also doesn't seem to allocate something. So the only functions that do something with the heap are malloc and free, and malloc is only called, I think I haven't checked. Yeah, it's malloc. If you look at the cross references here in the bottom left, it's only called when a new user is allocated. So and the other function that messes with the heap is free, and free is called from these two functions. So in this function here that calls free, if we follow where this is called, it's called from main, and it's called at the option 1. And the option 1 is delete user. So this function here, if delete user, will simply free the two chunks that were allocated. So now we have two interesting options. We can add a user and we can delete a user. And now we can think of how can we get to a heap layout that looks like this. So I mean, it's just iterative. If you just start thinking about it, it will come clear. So if you add a user 1, the chunk 1 that we control and the user 1 will be allocated if you add the first user. Now, clearly, if you would free that again, that doesn't help you much. So we leave that for now. So then we add a second user. So if we free the second user, it doesn't help us much. But what happens if we free the first user again? Then the heap layout will look like this. It will have free space above the second chunk. And if we now allocate a third chunk of the same size, it will just be placed here again. But we do control the size of the first chunk. So if we actually make the chunk then bigger, so chunk 3 will spawn actually across across the whole area before, then the user chunk 3 of the fixed size 80 has no space in here anymore and has to be placed afterwards. And then we have exactly this condition that we wanted to, that the chunk we control is placed at the beginning and is wrapped and this wraps then a complete other user that we have allocated. And that is basically the trick of this whole binary. So if you somehow get to this part, you're basically there. Now it's just like manual labor to actually implement it in this way, because then this means you can control the pointer. With the control pointer you can write somewhere. With the pointer you write somewhere, you just like overwrite something in the global offset table and you are there. So let me move I kind of forgot to move it forward to debug the red ball. I guess yeah, let's put it to debug, because now we want to like start scripting this and like get to this condition and then we go from there. To simulate the CTF server that you connect to with Netcat, you can just like run the challenge yourself with SoCat in a different terminal. So let me quickly start. That's so SoCat, and we want to call the babyfengshui patched. So now if we netcat to localhost port 2323, we can, this program gets executed and we can interact with it. That is how basically the challenge server would also work. You could connect to the server that is listed here. So we can just like leave that open, but don't really care much about it. Let's just put it into a different tab and ignore it. Okay. So also the IP of this machine is here, so we should also be able from, so on the right is my Mac terminal. We should also be able to I guess I didn't set up the VM network properly. Or is this just listen on? Nets, oh god. No, it should listen on. Okay, yeah, I don't know what the I didn't set up the VM network probably. Okay, then we gotta do it all on Linux. So let's start basically writing our exploit. So first of all, we wanna connect. So let's yeah, I guess let's leave that here. So first of all, we want to interact with the server, so we import socket. Okay. If you have questions, write it at live overflow so that I can see it. Okay, so import socket. So we open a new socket where we just like I gotta Okay, and then we connect to localhost port 2323. Yeah. So then I create a function receive all. I've used like these kind of snippets already in my videos before, so maybe you are familiar with this already. So I just define a function like receive all, where I will just like, it's really not pretty, don't judge me, like this is not how you do network programming, but it's quick. So I always receive a byte and append it to the output, and I do this as long until there's a timeout. I guess I should also set the set time out of the socket. So it will read 1 byte until it receives the timeout, and then it returns how much byte it already got. So if we print receive all, so this should now connect to localhost and just print the menu and read the menu. I'm sorry. So we got it. Got distracted by chat again. Okay, so when we execute now heap, it should, it connects to the service and prints the menu. Great. So how now we just have to basically program this to get to this stage here. So what we want is first of all, we want to send a 0 to add a user. So we can just like send a 0 with a new line as if we would have entered it ourselves. Then it asks for size of a description. So we can just like 16. Then we just enter something. So size of 16, then AAA. After that, it asks for the text length, which I don't know, doesn't really matter. Like this. So 8 and AAA. So now we added 1 user. But if you remember, we first want to add 2 users, so we basically do exactly the same again. That's just so that we can recognize it in case we want to look on the heap with other characters. Let's do it all capital. So now we have added 2 users of the same size. Let's just try this. What I do is I use raw input a lot, which just like pauses until you enter something in Python. So if we now connect to it, it will just wait and quits when I press enter again. So now the process is still running, which means we can connect to it with GDB. So PID of so this is the current this is the current process that is running the babyfengshui version, which is like hanging here still and waiting for that we do something with it. So we can just attach GDB to that PID. Could not attach to process. Sudo. And then we can look at the heap, and you can see here our 2 objects, the A's and the B's. Cool. So now what we want to do is we want to free the first user that we added to create a hole at the at the top that can then later be filled with chunk B. So how do we delete a user? We just send a 1 and then the index. So we send a 1 and then the index, and we want the first user, which is user 0. So now there should be a hole where something new can be allocated. So let's add here some prints, user 1 created, user 2 created, user 1 deleted, and now we want to create a third user, but this time we select a bigger size here. So let's just do like size. Is that the correct size? Wait, yeah. So we just allocate now a bigger size so that not both chunks have space in the free one, but the C one has to be placed at the end. So let's try this. So this should already be basically our exploit condition if I didn't make any mistake here. So we do a raw input again. That was stupid. I wanna Python. Here we go. So it should have now deleted. That is, it should have user created. So we connect to it. We look at the heap. So there's also ASLR. So the heap will be somewhere different every time. So let's have a look. And this looks really, really good. Let's have a closer look at this here. So that is the current state of the heap after we have carefully created and deleted users. So let's just draw this here out so that you can understand this. So first of all, the B's were the second user, right? So you can see here, this is the first chunk with like the text description thing of the second user that we created. It goes like this. And then the big 80 hex fixed chunk, like the user object, that is like this. So this is our second user. And the first user is obviously freed, so the first user doesn't really exist anymore. But where's the third user, which we added with the C's? If you already see here are C's and here are C's. So as you can see, it's split up. So here's the first chunk, which is now a little bit bigger. Wait, I'm a bit confused. Okay, like this here. There you go. So this is now the C chunk that got allocated. Here are our C's. But the second part of that chunk is here. It's after the second chunk. So this goes like this. And here you see the pointer, which points all the way up here. So, and now if you remember the check with the lead check, it would take this address. If you request a certain text size you want to write, it would add the size to this address and would check that you don't reach into this here. But you can perfectly fine reach into this here and completely overwrite this. Thus, you can overwrite the pointer here. We can also try this and just like trigger a seg fault next and go from there. Okay, there we go. So so now we created the third user. And what we could do next is we edit the third user. And editing the third user was which option? I already forgot again. The third option. So now we wanna and then how does this work again? Like what does edit mean? We update the third user, select the well, user doesn't exist. So we want to update the first user, then select an input length, which in our case would be super huge then, and then the text. Okay, so we want to first send action 3. We want to send index 0. Then we want to send a text length, and this one is now the key. That one should be very big. Now, obviously not too big. Let's just hope that this is enough. I don't know. It should be enough. And then we send. Let's send these to see what we have written. So like 26 Ds, 62 Ds. And then let's actually do the interact afterwards, as we can then interact with the code. So that would be import telnet lib telnet socket and interact. Oops, that's fine. So we execute the Python program again. Obviously something is going here horribly wrong. What just happened? Okay, what did I do? So we execute it. It creates the third user successfully. It's waiting here now, and then it edits the user. Okay, fine, and then okay, this interact thing is just breaking it. I don't know what's happening. Okay, let's do this again. Okay, so this is not causing an endless loop. Okay, so we are created, edited, and now we can connect again, attach to it with GDB. We have a look at the heap. And that clearly did not work. So what happened? Update, the third user is obviously index 2. Now probably the interact would also work. No, I have no idea why not. Okay, so let's check again in GDB if this time we actually have written the characters. We look at the heap again. No, it did not write them again. Wait. Let's ignore this very quickly. Okay, so we want to update user. Oh, we don't want to update the 0 user. We want the third option. We don't want to update the first user. We want to update the third user. There we go. uncomment this again. There we go. So now let's have a look on the heap. Now this should be fine. Yeah, so we have here written a lot. Did we reach the part that we actually wanted to control? No, we are still way too far away. Okay, so wait, let's do some math really quick. That was obviously stupid. So we want to reach up, like up to here is fine. And we are coming from here. So those are 176 characters we want to write. So let's do like 180, 76. Let's try this again. Let's execute. So it should be edited now. We connect GDB. We look up where the heap is. We look at the heap, and we have overwritten a lot of crap. And clearly, we have also overwritten here the pointer. Now, if we have here now the menu where we can do an action. Now let's try what happens if we try to update the user description of the second user, which's address we completely wrecked. So we want to update a user description. We want to update the second user's description. This is index 1. And we say a text length, how much we want to write. 4 bytes is enough for us. What did that happen? What did I do? Wait. Why did that? Oh, I get it. Understandable. So the address 4444 is super huge, right? So it took this pointer. So if we think of if we look at the function that is responsible for reading, doing this, what we talked to with the lead check. If we look again, what it's doing, it takes the address in EAX, like that is the current address that it read from the heap. In this case, then 4444. We can actually let's set a breakpoint here. Let's like step through this. So we execute the Python again. We attach to it. We set a breakpoint there. We continue. We step further. We edit it. Not this breakpoint. So now we update the user of these. We update the second user with 4 bytes. Now it triggers the breakpoint. So we EAX points into the heap. This is where these Ds are stored. So these Ds have overwritten the other user. So this is the one user, right? And it takes now the address that is stored here. That would point to the other to the other chunk like before. So if we step one step further now, EAX contains 44. So it thinks that is the address where the other chunk is. And then it does this check where it takes the size that we used, which is now loaded into EAX. So we entered, we want to write 4 bytes. And then it adds the 4 in EAX on top of the address that we had, which is 404, which is fine. Now it's pointing here. And then it loads the address of the chunk again, and now does the compare, is this bigger than this? And then it obviously will fail because this is just the 44 is way beyond this here, so it obviously the check will fail. But it doesn't really matter because if you look on the on the addresses, the heap will always be a higher address than the other, in this case the other, the address where the Feng Shui binary is loaded and where also the global offset table is stored. So the global offset table will always be smaller and will not be as big as 4444, if that makes any sense. Okay, cool. So now let's again have a quick look at the heap. So 4, 8, 12, 16. So if we subtract 16 from here, so 60 plus 1, 2, 3, 4. Let's test this. This should just write the address here. Let's look at the heap. Yeah, looks like it. So here we have it now. This written, and that's fine. Okay. So one other thing is, let's actually check like the. I don't have check. Damn it. How do we do this? Check sec. Oh, yeah, no. God damn it. Bad mistake. Okay. So I just wanted to quickly check the mitigation issues. There's a cool script called checksec that quickly shows that for you, but we can quickly verify if ourselves, if like there's I mean, there's probably a better way. There's probably some people who know it better. But what we can just do is we spawn the binary once. God damn it! By starting our exploit, then we attach to it in GDB. We remember where the addresses all are. Then we simply execute ours again, so the program will again will be completely new executed. So the addresses, if affected by ISLR, should be different. So now we look at those mappings, and now we can just compare. So we see that the binary itself will always be at the same location. I mean, you could already tell that by hex 804. Like, if that's like the that's a typical base address for 32-bit, so you could already see that kind of. But yeah, so these are fixed. The heap will obviously be always in a different place and has ASLR, but we don't care because we don't care about addresses on the heap because we want to write somewhere completely else. And obviously the they are in fact also, they are not randomized. The stack is, but in this case the libc is also not randomized, but yeah, whatever. So in this case, okay, the libc is not randomized, but we also want our exploit to be working on on a different system. So it's generally always, and it's weird. Like I would have expected, I guess, I don't know. Somebody who actually knows stuff can maybe explain to me why it's not randomized. Here it's randomized. I don't understand. Anyway, it's better if we just leak a libc value, then calculate offsets and do all this kind of stuff. So let's have a look at what kind of function we might wanna we could leak from the global offset table. So we can have a look here in the global offset table. These are all our functions that we could get leak libc addresses from. I don't know, like malloc or something. So let's take this address and we plug it in. I guess we need struct. We plug it in where we overwrite the address here. So now the this one object points into the global offset table, and then we can test this. We can read from it if we display the second user. See this description, because it follows that pointer points into the global offset table, and these are actually libc addresses. So we can just like can use the receive all function we received before, and then we leak some data. So let's have a look at what this data, what we actually leak. Obviously print. So we want to display user 2. So we send the command, the action for display, which is 2. And then we want to display the first user, and then we have a look at what is returned at the sec. Why does it come afterwards? Is it just a... Oops, I'm stupid. Leak. Okay, so now there we go. So here you can see already like the libc addresses F7, G, F80, whatever. So that should be the address of malloc. Let's actually make this proper. So this is malloc in the global offset table, has this address. Read that. 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That's ugly, but doesn't matter. So 20 to 24 should be our malloc address. Yeah, this looks good. So we can struct unpack. We interpret this as an integer, so that should be malloc from the libc address of malloc. Was that not? Oops, the presentation. Okay, so now we print leaked malloc address, and we can then just like display this address as hex. What's going on? Oh, there we go. So that should be our libc address. We can kind of verify this now. We attach again to this process that is still running there, and we can like, first of all, we can like look ourselves at this address if that is really what is there. So this is exactly this value that is stored there. So perfect. And that is malloc. So if you print this address, GDB recognizes that as malloc. Okay. So now that we have malloc, we want to calculate the base address of malloc in libc. How we can do this is, so first of all, the challenge itself came with a libc. So if you would then actually do this against the challenge server, you would have to also get the offsets of that libc. In this case, the server is, I think, not running anymore, but basically extracting these the value that we will do now is basically the same for your local one as well as for this remote libc one that is provided with the challenge already. So we want the offset of malloc inside of libc. How do you find your own libc? What you can do is basically just like use LDD on this binary, and it will tell you where it will get the libc from. So that is the binary, that is libc of your local system. Well, it's a symlink to where it actually is. So it's pointing to libc to, yeah, there we go. So that is the libc. So let's just copy these to the shared folder so I can then open it up in Binary Ninja as well. Then we just have to wait a second for it to analyze. Let me quickly check the chat. Way earlier was a question why I'm using Binary Ninja, not IDA. I cannot use any of these tools like very well, so I just like jump. Sometimes I have a phase where I try to understand IDA better. Then now I'm just like in a phase where Binary Ninja is fresh and new, and I'm just like to use it. It just looks neat. I don't know. Like for these kind of challenges like this now, I don't need any of the fancy features of IDA that I don't know how to use anyway. So, and also the Slack Binary Ninja channel is pretty cool. I really like to hang out there. There are a lot of people that are very helpful, and it's just a cool community around Binary Ninja. I quite just enjoy using it for any professional work with serious reverse engineering. It's not there yet. But for like this kind of CTF level that you needed, it's pretty good. Can't wait for the structures to finally be implemented. Anyway, so here's the address now of malloc. That is the offset. It ends in 30, so that makes sense. So the offset in libc for malloc is this one here. So we can now calculate also the libc base based on the malloc libc and subtract from it the offset, and then we can just like also print it. So let's execute this. So this is our calculated libc base. We can verify this now by simply attaching again GDB to this process. When we look up the where everything is loaded, and you notice that here this address is here. So this is where libc is loaded. So this is correct. So this is the correct offset. We calculate now the libc base. Okay, cool. So now it's a question, what kind of function do we want to overwrite on the on the heap. Does it make sense to overwrite malloc? I guess it doesn't really matter. We just want to trigger just something so we can overwrite malloc. That is fine, I guess. And then we trigger adding a new user, and then we are there. So we leave it like this, and now it's the question where we want to write to. Let's first try to redirect code. Maybe I should have done this earlier. Let's try to redirect code execution by editing the second user, which then would follow the pointer and write into malloc. So we want to edit the second user. We only want to write 4 bytes, and let's just like write AAA there. So let's execute it. Okay, that already broke. Let's see what went wrong. Let's attach to it. Continue, let it run. Already got a segmentation fault for 4 because it tried to reference here values. Where are we? This f gets. Why did this happen? We want to update the user of the first one. Wait, let's do this by hand really quick. Let's connect to it. No. We attach GDB to it, and now we select the first. We want to edit the first user. We want to write 4 bytes, and we want to write 4 characters AAA. Why does it crash in fgets? In p open? Hey, wait, what? No, wait, I'm confused. I doubt anybody was able to kind of follow and tell me what I did wrong here. God damn it, what did I do wrong here? Okay, so we overwrite. Let's check the global offset table really quick if we did overwrite this successfully and this happened later. Where's my mouse? There you go. So let's look at the global offset table that we hopefully have overwritten. Okay, so we did write something to the global. Oh, I get it. So we wrote 4 characters, and after the 4 characters is a null byte, and so it overwrite also the address, a part of the address of the global offset table entry afterwards. It wrote there a 0. So if we look, why did I call this? Wait. So if we look at the global offset table, what comes after malloc? It's puts. So it overwrote and part of the address puts, and that killed it. So actually, and then it wanted to call puts to print something, and then the address was incorrect, and it jumped in the middle of some garbage, and that's why it crashed. This means we do wanna write to a different address. We should be just able to copy this, and instead of malloc GOT, I guess we write to put. So let's put the address +4 there, and then so now we should have overwritten again the address of the second user by editing the third one, and we then edit the second user, and then we want to write 4 to the new address, which is shifted +4, which should now overwrite puts. So we send now AAA and a new line. But we should just just before we do this, we wait. Okay, so let's try this again. We execute this. Let's connect with GDB to it. If we look at the global offset table, it's not overwritten yet. So we continue. And now when I press enter, we should edit the user 2 and write 4 bytes at its address. Segmentation fault in address 41414141. You see the instruction pointer got overwritten 41. It has now 414141 because if you look at the global offset table, the address for puts points now to 414141. So now we control the instruction pointer. Now is the question, what do we want to write there? What we did during the CTF, we were looking for a so-called one-shot libc gadget or whatever, like a one-shot bin as exec bin as ha gadget, so to say. If you haven't paid attention until, like, if you just faded away, now is the moment where it makes sense to quickly pay attention, because like this is I didn't know for quite a long about it, but it's super handy if you know about it. And that is that often in the CTF challenges, it's enough to just somehow execute a shell, like for example call system or call execve or something like this. It executes a bin sh or bash or shell or something. And then because you already have this interactive netcat like open, you can like just then use that shell over the network. So that is very convenient. Now it's the question just how do you execute the shell? And what you can do you can build a rob chain that would call this. Maybe there's a very convenient function that you can overwrite with system. I've done this a lot during my videos where I would like overwrite, for example, a printf with system, and then every time printf would be called, it would call system instead, and we control what printf would print, and then you get the point. But there are you can also find so-called one-shot gadgets that just do that for you, like execute a shell. And let's try to find one of these. How we do this is we can just like look for all the strings in the binary, and we want to look for bin sh. I actually don't know if we can find it with Binary Ninja. So here we found bin sh, the string in the binary. Oops. But we can't find any cross references. Let's actually use IDA for that. That's why I have IDA open here, because somehow like this is where like Binary Ninja sometimes like still suffers a little bit. But so I'm opening now the libc, but my local libc, obviously I would also have to do this for the wait. Did actually the remote server and me have the same libc? I guess so. So copy libc. So this was my libc. Just notice that the other one is gone. So they had the same name, right? And I think I have the unpacked one somewhere. No, okay. Same name, but they are different. So you would have to be careful. seems to be the same version, but different hash, so offsets might be different. Anyway, so I'm opening now my local libc, and you would have to do this with the libc that is provided with the channel as well if you want to make it work for the remote server. We are now letting this analyze really quick, and while this quickly runs, I quickly check the chat. Why do I not create a Discord server? We could ask questions or post crack me videos, stuff like that. Just do this on the subreddit. Like, this is not a big community or anything. I don't like. Just like post the stuff on the subreddit, and I will just delete it if I think it's stupid, or like people will downvote it if it's stupid, or if it's great, people will upvote it and comment on it. Like just post it. Like I want to use this subreddit kind of a thing. Then it's also there for prosperity if people at some point want to like look up something. Okay, so let's look for all the strings. We look for bin_sh, for example, here. Now let's look for cross references where this is used. So let's look up here, the first location where bin_sh is used. And we can see here that bin_sh is loaded in like EAX, some place somewhere, and then it calls execve. So this sounds already like very promising that it might just want like it just wants to execute bin_sh here. Let's see which one did I use again. I've like made some notes here. So in my notes I have used. Oh wait, this maybe for the remote one. Wait, let's see if that makes sense, the address that I've noted down. Maybe that was for the challenge itself. So this location doesn't make any sense. The other location I have written down is this one here. Also completely doesn't make any sense. Okay, so that must have been for the remote service. So let's go back to the bin_sh here. Let's just try the first one. So where would it make sense that this bin_sh is set up? So it moves here certain. It does prepare quite a lot for it. So like I don't have the patience to now quickly check if that makes sense. Let's see if proc open makes more sense. So it will call here execl. I don't know. Let's just try this. So this would move it in. Just take this address here. So this would then be the libc base plus this offset that we've just found here. And ideally, like I don't know, that that's just like I'm not trying error. It would load bin_sh properly and then would call execl, which would then execute this. And this might work or might not work. Like I don't know, maybe it's not properly then set up yet and will crash, or it works. I don't know. We will figure it out. And we send to it struct.pack and then it should theoretically already work, I guess. So let's see what happens. I mean, it would be a miracle kind of. Oops. Wait, what? Oh, plus. So here, that string concatenated. Yeah, okay, it crashes. This makes no sense. Let's quickly check with GDB what's happening, why it's crashing. It does execute bin_sh, so that kind of works. It just still like dies. maybe we should, maybe it still doesn't like properly everything. Maybe like, let's see what happens if we go a little bit earlier. Okay, this, it dies 2. Okay, something it doesn't like here. Like, I don't know. See if we can make, let's see. I don't remember, man, exec L. What does it want? It wants the char and then the arguments. I guess there's just in some crap, not a, we have to make sure that there's a 0 on the stack. So I guess this kind of would make sense. But it also adds -c, which we don't quite like. Let's look for a different one. The first one here, it's maybe environ. Yeah, let's maybe just take this here because it seems to set the 0 here and then bin sh. Let's try this. If that offset makes more sense. Wait, malloc offset, that is incorrect. This worked. There you go. Cool. So this gadget here, like this address, we are jumping just like in the middle of this function here. And we'll properly set up, in this case, execve. If we look again what execve does, it wants a pointer to the file name, which in this case is then bin sh, and then a pointer to an array of arguments and pointer to an array of environment variables. And I'm kind of hoping that it would like set here 0 eax 0. Yeah, so we'll just set these to 0 to null, and we'll just exec the file name. Cool. Yeah, so here's our exploit. We run it, we wait, and then we have shell. And now if you would want to make it work for the remote service, you would open the libc that was provided with the challenge also, and then you get the offset of malloc, and you get your one-shot gadget, and it would work for the remote server. So that's basically Heap Feng Shui. So what do you guys want to, so I guess we're done with this, but it maybe makes sense to just like, do you guys want to like a quick recap again? Do you want to like talk about the idea of Heap Feng Shui, like what it, like I don't know, what were you able to like get the gist of it? Like, do you know what to look for when you, or do you have an understanding what Heap Feng Shui means? And did you not quite get a certain part? I'm sure nobody was able to, like, how long are we streaming now? Was able to just focus for 2 hours. That nobody can do this, like, unrealistic. But maybe somebody will like rewatch it or so and carefully. But what would be important for me is just like that you get, with listening once in a while, if you just got a rough gist of what it is about and what the strategy is and what the ultimate trick in the end was. Like, what, like, do you have a feeling for how we figured out what we wanted to overwrite and how we wanted to arrange the heap, and then in the end also like how we got to the actual shell once we knew how we can like abuse this thing? Like, did you like give me some feedback on that maybe? Let me just read a little bit of chat. Okay. The selection of libc function was confusing. Which part was it confusing of in like the global offset table? What I used to like leak address and which one I override, or the selection of this like this one-shot gadget I'm talking about, like where we are jumping to in libc and why we get a shell of that. Yeah, and you say that was baby. Yeah, I totally. It's more difficult than Web 150, for example. Yeah, I totally agree with you. I didn't have an easy time with Heap Feng Shui. It took me more than 2 hours, I think, with a friend together during the CTF. I'm still like not very quick. I still make a lot of easy mistakes, and just like these simple heap arrangements is already like still a lot of mental energy that I burn on this until I come up with this. And these 500 exploitation challenges are not reachable for me. Like this is inhumane to me. But I hope that maybe with like, I mean, I'm just not like I just don't get it as quickly as maybe other people. But maybe some of you are I maybe I can bridge the gap to get you there that you can actually do these baby challenges, because if you like actually do it, they are not that hard. It's just like, I don't know, the big CTF teams and the players that did for years, they just have a lot of practice, and it just takes a lot of time getting there. I'm hope that CTFs make more like these of the baby challenges. These are not the challenges that will decide which team will win in the end, but it's still very enjoyable and a very important like learning experience for people. Yeah, let's look at so I guess it was solved more times. I guess solved 78 times. 68 times. Yeah, I guess so. Was solved quite a lot. I mean, with a lot of things, it's like this CTF had a lot of challenges, and as a team, obviously, we covered a lot. But I personally, I had only time to look at baby feng shui, eat, sleep, pone, repeat. I did sit together with another friend at Smart Fridge, but we didn't come to the exploitation part, and he did most of it. I did participate a little bit in the 90s call. I think that was a really cool challenge. That was so much fun. I didn't look at anything of the crypto. As I said, like I did a little bit with Smart Fridge with a friend, but he did most of it. I looked at the list or web and YOLO Vault, which in the end, like I felt like I was close, and I guess I could have gotten it if I didn't have any time in the end. I didn't look at the forensics. I didn't look at the programming challenge, and I did work on like all the other stuff, like all the other ponables. I didn't have any time to look at, and it's just, I mean, that's why you work in teams, that you can cover all this ground. I mean, Web 200 solved 180 times and it didn't give small points, even though you could solve an absolute beginner within 10 minutes. Well, as far as I understand, most of the web, a lot of the web challenges were broken and had way easier solutions that was intended. So the Web 200, I guess, I don't know what I was here about, but maybe it was just because it was broken. There was a mistake. Can you show where in memory you were able to take over the control flow? Yeah, okay. So, first of all, taking over control flow, like this typical thing that basically we do in almost every challenge, is there's this global offset table, and that global offset table has pointers to functions in libc. And when you are able to write a value to that table, you just call a different address. In this case, for example, this binary uses here, these are these yellow functions. This is the table. Like, these are the single entries, basically. And this is used for like dynamic libraries, whatever. When the address of the real address where malloc is will be at this location, in this memory location. And when the program calls malloc, it will actually call this function here, and this function does nothing else than referencing the value that is stored in the table and jumping there. So it will reference the real address of malloc. So if you are able to write a value to this table, this jump, this malloc jump will jump to this address that you have written to that address here. So if you write there 41414141, you jump to 41414141. Now the challenge is then, how do you write there something in the first place? And in our case, we abused the option. There was this option to update the user description. And to update the user description, it took an address from the heap and wrote an updated description to that location. And in the bug that we exploited, we overwrote that pointer, so it pointed to somewhere else. It pointed into that table, and when we updated the user description, it followed the pointer. The pointer that we have overwritten is pointing now into this table. So we write a different value into this table here. In our case, we have written at the location of puts, where the address of puts is. And the next time, somewhere in the code where it would execute puts, let's see, where's the puts? Here's the puts. Maybe it would, no, probably not this puts, but it would just execute some puts. Let's go with this. So it would reach here, it would call puts, but what does it actually call? It goes into the procedural linkage table, where there's like this little snippet that just like says jump to the address stored in this table, and we have overwritten that value. It points now somewhere else, and it will like redirect to that location. Does that make sense? And where exactly we took over control flow, I don't know, but it happened obviously in the so we selected update user description, which is option 3. Option 3. So it would reference the user object of that user, and then the first, which is completely overwritten with our junk, and the first value of that user object is the address pointing to the description, and that is referenced here, and we control that address, that pointer we have overwritten. So that is pointing now into so EAX is the first address here, and it dereferences it, so it takes the value at where EAX is pointing to and moves that in EAX. So EAX in this case then is pointing into the global offset table, and then it performs a few checks, blah blah, and then it reads input and writes that at that location. Like here it gets it again, like here it takes the address, it places the address on, it passes this address to read input, so it will read into that location, and EAX in this case will point to the global offset table. So read input will then perform the fgets, and that will then overwrite, like this address will then be written over, will overwrite the global offset table entry, and then it goes down here. It returns from this function, and where does it return to? Read some text. This will also return. Wait, this I got confused. Anyway, it will at the next puts that will be called. It will then actually redirect code execution. A bit behind the stream is it like that a huge delay, or sorry, how would you go about exploiting an arbitrary write on a program that panics every time something in text or const gets modified? Do you mean that the that you try to write something into non-writable memory, or like if you say text, you usually are you referring to the like the text segment where your code is? Like if you look at this running process now, the text segment, like do you mean this as a text segment, which is like how do we does proc show it, the permissions on? Yeah, so the most of the binary is not writable. You are not allowed to just overwrite code. Like this is where the regular code is written to. You can't overwrite the. Oh, okay, yeah. So I mean, in like depending on how you compile your program, you can also enable what's it called? You can also make that the global offset table is not writable anymore after it got initialized, and then you can't do that technique anymore. But what will always work is as soon as you can like defeat the ASLR, you can always build a ROP chain to then just do your bidding, or I guess Niklas says VMAP, you can just like change the oh, is that? I mean, there's must be some kind of system call to change the permissions on segments. Oh, yeah. Okay, gotcha. Thanks. So he was saying that in VM. Ah, there we go. Oh, cool. Thank you. Yeah, I don't know my like I'm not very good with tools. I have no idea about these things. Thank you very much. But I think it like at least on Windows, like it's like as far as I know, I have almost no experience with Windows, is that you like usually try to build like a ROP chain that would like change the memory protections of the thing that you can then write your shellcode to and like execute it. I think something similar should also be possible in Linux, I guess. So you're asking about your problem. I just put stuff on a stack and build a chain. Yeah, I guess, like, I don't know, like how complex or like, or if you even can control the heap or something, I don't know. Like it's just an arbitrary write, so I don't know where you want to write to. But Niklas B says something important. There's, for example, the free hook. If you like look at free, if you just like so there in free, there's literally like it will call a value that is referenced from somewhere, and that is the free hook. You could like write code like in I guess, I don't know, is that the name? Free. There's you can set a free hook that would x here. If let's just set this value, for example. I'm so bad at this, like the syntax. Did it work? No. Okay, so now the free hook is something, and if you then shit. Call, does this work? I guess not. Anyway, there's like it will there are some constructs like this free hook where that would be called if free gets called. It will look up if there's a hook set for the free call, and then it would execute that. And Niklas has definitely way more experience and can tell if that's like always there, or if like 40 like this thing that would make GOT not writable, if that would also take care of something like this. I don't know. Like probably Niklas knows that. Yeah. So I don't know. I'm basically done now with the thing. Again, it was like similar to the last stream. It was a lot of rambling and obviously not as concise and straightforward as video, and it took again like 2 hours. Okay, so and Niklas says the railroad only protects GOT. Okay, yeah, then I guess if your program uses free, and you can, I guess, write a value to the free hook. Yeah, so if there's anything else, like if there are some more questions, or especially yeah, if there's nothing left, then I just wait for another 5 minutes. If some questions come up, just otherwise then we call it a night. Maybe this Chris again. Anyway, follow me on Twitter, share the videos to people that might be interested in something like this. What I really would like to do is, if anybody of you ever finds a cool bug, an interesting vulnerability, like, it doesn't have to be like a crazy root exploit or whatever, like just something quirky, something interesting, something that like gives you a deep understanding of some kind of software or anything. Like if you just find something like this, I would love to make videos about these kind of things. And I mean, as an example, you can take Dirty Cow, but obviously that was a huge thing. It doesn't have to be anything like this. Just if you find something that you like, that you're proud of, that you found or something, like maybe we can do, like, I would love to make videos about something like this. Also, I heard from some people that they don't want to do own video recordings of CTF challenges because they think like I have now the monopoly or something on this, and it's absolutely not the case. I'm encouraging and I hope that more people will do this, because I make these videos because I would like to see them, and so if somebody else would make videos as well, that would be highly appreciated, because then I can also learn from them. And so if you feel motivated, that would be really cool. I would really enjoy watching that. And feel also free, if you do create videos, to share them just on the subreddit. Just, you know, like, we are a small community that there's not really spam or whatever. Like, who cares? Just if you think you found something cool, just post it there. If you created, if you have written a write up, or if you have filmed yourself or whatever, you can just post it there. That would be really cool. Here's somebody, Svetlin Konarov, says he is apparently a cool jazz. So I don't know. Like, look it up, post it on in the subreddit maybe. Otherwise, I miss these things too. Yeah. So this stream took me now, like, if we just opinion wise, I'm also curious. I'm streaming now for over 2 hours, with like preparation for it. It also is like 3 hours or so, I don't know. It doesn't take as long as it takes me to edit a full, like, regular video. Do you like to have a balance like this? Do you think something like this actually works in a streaming format? Personally, like, I probably wouldn't watch a 2-hour video of something like this. I very much would prefer a short episode, but maybe for some people a stream is more helpful and can be more engaging. If, I don't know, maybe also this kind of topic is not very suitable for streaming, and maybe a web stuff would maybe work better for a stream. So I don't know, if you have feedback in that regard for me, that would be very helpful. I think some kind of balance would be nice. I do quite enjoy a little bit of rambling as well, but I don't know, I personally wouldn't necessarily watch a 2-hour video of, like, doing this, because it could definitely be condensed and explained in 10 minutes what I just did in 2 hours. Thus, I obviously prefer the shorter one. But yeah. So, and maybe before I finish this off, let me figure out how, like, the spanning and reporting thing works. Okay, I guess it's simple. Maybe I should have done this during the stream. Anyway, okay, thank you very much for watching. Again, interact with everybody else on the subreddit, on Twitter. Share some of the videos with other people that think maybe are interested in it. Create your own content and videos. I would really like that. If you have an idea for, like, collaboration or something, like, I would just like to see this grow. I think it's an amazing topic to learn about, and it's highly rewarding, I think, to solve these kind of challenges. And I just wish more people I'm sure there are way more people that would find this enjoyable and just haven't discovered it yet for themselves. So also together we can, like, push each other forward and get more advanced together. And I don't know, like, this is sort of my overall vision. That would be really cool. So if you do your own stuff, that would be cool, and we can, like, do something together as well. And that's all, I guess, what I have to say. So thanks again for being here, and see you hopefully soon.